Hello everyone. Today we will be talking about oceanographic data visualization and comparison using a common geo-browsing platform. My name is Sydney Crane, and this project came about because it is my capstone project for the ocean engineering program at the University of Southern Mississippi. So just to kind of give an overview of the things we'll be discussing today, I want to make sure that we're all on the same page when it comes to data sources, retrieval, and manipulation. Then I will present my scientific question and answer. I'll give some project-specific details. I'll tell you how I would like to automate the process of retrieving data and manipulating the data. I'll present a little bit about GeoBrowsers and KML or KMZ files just to give you a background. I'll show you my website and give a brief tutorial. And then we'll have conclusion. I'll show my sources, and then we'll have time for question and answers. So let's get started. Like I said, first is data sources, retrieval, and manipulation. So some common data source examples include ocean models, observational instruments that are housed on ships, autonomous vessels, buoys, or other ocean instrumentation, as well as satellite data. These are just a few of the resources that we have out there. The two that are most common to me that I work with often are HICOM, which is the Hybrid Coordinate Ocean Model. They have model gridded output for regional areas as well as globally. And then also I work with information that comes from the National Data Buoy Center often. This is a federal organization which has buoys worldwide. So now that we've talked about this, let's get into how we actually get this data from these sources. So this can actually be a pretty time-consuming process, and it's usually kind of interactive, but there are ways that it can be automated. But I just wanted to show you the web interface for while you're trying to download. If you're not a part of the scientific community who works with this sort of data a lot, all of these different options that you have to choose from could probably be pretty overwhelming. I know they were to me when I first started working with this sort of data. For HICOM, you have all kinds of different variables you can choose. You can change your time, your vertical level, the area that you would like to download from. And then for NDBC, there's different types of data. There's meteorological, wind data, wave density. As you can see, there's a whole lot of variety here. And if you don't know exactly what you're looking for, it can get quite confusing. So now that we have the data and we've downloaded it, we'll talk about what happens next. So first we process it. We get ready to do statistics and get ready to plot and visualize. So the types of statistics that we do, just to kind of briefly go over them, include things like correlation coefficient, standard deviation, root mean square error, and then simple things like finding the maximum, minimum, and mean. And then we visualize and interpret this data. So I'm in an internship with the Naval Research Lab, and this is a plot that I created for those purposes, just to kind of give an idea of what types of plots we create. So this is a time series of sea surface temperature in the Gulf of Mexico at a specific buoy location. This one's more towards the western Gulf of Mexico, and it's for the year of 2019. We have 3 data sources here, and as you can see, they kind of closely line up with each other. Unfortunately, there's several months here where our buoy was actually not reporting any data, so we can only compare it for the last few months, but that's how it works in the world of science, is sometimes our instruments fail us, and there's not a whole lot we can do about it except work with what we have. So comparing the model data to our other data source, ERSST, you can see that the model doesn't quite predict such drastic crests or troughs. but overall there is the same curvature of the line. So these are just the kind of statements and understandings that scientists would try to gather from a plot like this to judge the model performance. So now that we've covered that, I'll get into what my scientific question is. So I want to know if this process that I just walked you through can be automated, which would give access of scientific data to a larger audience, but keep it user-friendly and free. And the answer here is yes, it absolutely can. And here's my idea how. So just to give some proof of concept specifics, I did have to narrow the scope of this project before I embarked on this journey so that it would be doable within the time frame that I've been given. So the region that I'm looking at is the Gulf of Mexico. This is where a lot of research occurs in the School of Ocean Science and Engineering at USM, and so it's very important to us. The variable that I'm looking at is one-dimensional sea surface temperature. The data sources that I will be pulling from, as I discussed previously, are HICOM and NDBC. I'm using MATLAB to write my scripts. I'm borrowing USM servers Triton and Medusa, and my output will be KMZ files. So automating the process begins with retrieving the data. So accessing the buoy data is pretty straightforward. They have a latest observation link, and this can be accessed every hour on the hour, and it actually fetches the most recent NDBC data that is reported for active buoys. The next thing that we have to do, though, is access the HICOM data, which is not as simple as just going to a link. The link actually has to be built by using time variables, but it's still completely doable. And so this link that I've built here will fetch the data for a day-long forecast, and I'll access this link every day at midnight, and then as the NDBC data comes in, it will be compared to the HICOM data that we already have. So now we just have to make sure that the data matches correctly. So first and foremost, a box per se is drawn around the NDBC data to only keep buoys that are within the Gulf of Mexico. And then thankfully, this link that I've created actually only downloads HICOM data within the Gulf. So as you might have seen when I introduced these two data sources, the NDBC data can be thought of points like buoys in the ocean, so it's a point, whereas you could see in the picture previously that the HICOM data is more of a grid. It covered the entire Gulf. So in order to match the data together, you want to make sure that the model data is matched to the observational data. And to do this, we use bilinear interpolation. So the figure that I put to the right kind of shows this. The 4 points on the outside of the square can be thought of grid points from HICOM, where the buoy is kind of somewhere in between all of those points. So in order to get information from the buoy that's in the middle, the black dot, it's somewhat of a weighted average of the 4 rectangles, the pink, green, purple, and yellow rectangles. So once the weighted average is done, we can then get information about the buoy that's in the middle. So that's how we get information for HICOM at specific buoy locations. The next, however, is that HICOM data is reported hourly, and it's pretty consistent, whereas NDBC data comes in more sporadically, so it doesn't always get reported every hour on the hour. In order to rectify this situation, like I said, we match model data to observational data, and this is done through nearest neighbor interpolation. So I've included an image that kind of helps you visualize what I'm talking about, but just to explain in words what we're doing is that say that NDBC data is reported at 11:45, but we have HICOM data at 11 and 12. So the nearest neighbor interpolation finds the closest time to 11:45, which is 12, and returns the HICOM temperature that was reported at the closest time match. So that is then the time that the temperature that we use to add to our time series and to use for our entire system. So the next thing that we do, now that we have the data and we've matched it up, we do statistics on it. So the two statistics that I'm interested in for this system are root mean square error and absolute error, and you can see their calculations in these figures. Just to explain what the different variables mean, in the root mean square error, we have n, which is the number of samples taken. The predicted value is the model temperature. The actual value is the buoy temperature. And then going down to absolute error, we have x naught, which is the model temperature, and x, which is the buoy temperature. So thresholds based on this root mean square error are used to judge the performance of the model prediction against the observational result. So I do this by calculating the root mean square error for the latest 6 months. So that means N is hourly data for the latest 6 months. And then all of the root mean square error gets averaged together to get an overall error in the Gulf of Mexico. And so the current system looks like this. If the absolute error is less than or equal to 1 times the root mean square error, the model is green, or the buoy turns green on the map. If the absolute error is between 1 and 2 times the root mean square error, that means the model has done okay. If the absolute error is greater than 2 times the root mean square error, that means the model didn't do too well. So now that we've done statistics, it's time, well, let me add this last piece, that these parameters were decided after doing a historical study, using the same resources, just only using models or buoys that had historical data. And I also read pieces of a research paper where they discussed similar thresholds where a small absolute error in the Pacific Ocean was about half of a degree Celsius, whereas a large root mean square error was about 2 degrees Celsius. The historical study that I conducted, the small end of root mean square error for the Gulf was about 0.3 and the large end was about 0.55. So if we compare that to the thresholds from the paper, the system that we have in place might actually be a little bit more strict than what they're calling large root mean square error. So that's why I did decide to keep this threshold system. If you would like to learn more about that paper, the resource on the resources page at the end, it's listed in the citations. So now that we've discussed this, we need to talk about how the system runs automatically. And that is done by computational scripts have been placed on USM's Linux server called Triton. And then by the use of Chrome tabs, this system runs every hour on the hour. And then these files get placed in a proper directory on Triton, and then bash scripts will sync the directory on Triton with a directory on another server called Medusa. And by use of threads, these files will be made available to the public. So now that we've walked through the process of my system, I'll just introduce what the actual output is by first talking about GeoBrowsers and KMZ files in general. So what are they? Well, a GeoBrowser is Google Earth, and a KML or a KMZ file is just a file that can be opened in Google Earth. So just to give a brief example before getting into my project-specific examples, this right here is a GeoBrowser. It's Google Earth Pro on my personal computer. And then as you can see, there's some information stored here about the University of Southern Mississippi Golf Park, where I go to school. So the pin here shows the location, and then this description bubble shows pictures or other information about that location. So any type of information stored within the pin and the bubble are what would typically be stored in a KML file. And then the map that it's shown on is the GeoBrowser. So why does this matter to us? Well, my KMZ files that I'm producing are used to store the statistic information that I previously discussed. As I mentioned, I have built a red, yellow, green, gray system. And here is an example from May 4th, 2021 at 2 p.m. using the RMSE thresholds that I discussed on the statistics slide. In the places where buoys are red, the model predicted poorly. In places where they are yellow, it did decent. In places where the buoy markers are green, it did pretty good. And then if the buoy marker is gray, that means that data from one or the other sources was unavailable. I've also included here a sea surface temperature map to help users get an overall understanding for sea surface temperature in the Gulf of Mexico, as well as a legend to remind users what the buoy colors mean. And then in the description bubble, there are temperature readings from both sources, so that if you would like to compare on your own, you can do so as well. Also, if you look to the left, you get a list of all of the elements that are within this KMZ file. So now that I've presented this, I would like to kind of shift gears and give you a brief tutorial of what my website is. Before doing so, though, I will say that there are a few slides within the PowerPoint that are being left for reference if you would like to come back to the PowerPoint in order to just have reference after I give this tutorial. So once we come back, will just be my conclusion. So going to the HTML page that I built, I have just included the title of my project, a graphic that shows users that I'm pulling in data from HICOM and the National Data Buoy Center, and it is being displayed on the map in this manner. I've also included my abstract along with an at-a-glance section just in case users don't want to spend all of their time reading the abstract. They can just glance through this. My point of contact information is listed here, as well as how to access my data and how to access the source data. So there is a link for if you're on the USM network. If you're at home on your own Wi-Fi or somewhere else besides USM, this is the link that you'll follow, as well as a few notes here asking users to be sure to look at the README file and to please view these files in Google Earth Pro, which can be downloaded at that link. And then if there's any more information that's needed, you can always reach out to me or watch the YouTube video found at the link here. So now that this page has been covered, I will navigate to my actual website page. And so first we'll start by going to the log file. Just being very upfront, there was a glitch in my system last night. It did not run after midnight. So I was able to check on it today before the presentation, and I got it to produce a file. But as you can see, there's a gap here between last night at 11 o'clock and today at 10 a.m. So, but this file just basically keeps track of exactly that. So it's doing exactly what we want it to do. So now by navigating back, we'll take a look at the README file next. So this README file hosts a lot of information that is already in the HTML page that I already showed, such as the name of my title, my abstract, and at-a-glance section. But just up here, I also wanted a user-friendly way to let people know whether or not this system is active, inactive, or retired. I don't expect it to be inactive or retired anytime soon, but I don't want anyone to be waiting for the next file to come and it never come. So I'm sure that they would figure it out on their own, but I feel like the courteous thing to do was just include that little piece of information that's very simple to add right there. So like I said, I also have my point of contact information here, as well as an about the file section, just letting users know that they are written in keyhole markup language. And if they'd like to learn more about this file type, there's a great tutorial that Google has on their website that can be glanced at. I've also posted again that these files should be viewed in Google Earth Pro for best results. I let users know that the files are labeled with the following format: GOM for Gulf of Mexico, and then a 4-digit year, 2-digit month, 2-digit day, and 2-digit hour. And I've also mentioned that the Gulf of Mexico sea surface temperature log file has been placed there to let users know the last time that a file was produced. And if this was not on the last hour, that my system is experiencing difficulties, to try again or reach out if the problem persists. I also included some information about the buoy marker colors. I want users to just really understand how they're chosen, and if users don't like this system, then they can make their own decisions about how well the model has been performing. The red, yellow, and green are very subject to interpretation, so it's good to just have this posted everywhere. Some disclaimers that I felt like it was important to include are that these files can be viewed in Google Earth on the web, but certain elements are not displayed properly. The color bar for the color map actually can't be seen after you open it. I'm not sure what's going on there. It kind of gets hidden, so please proceed with discretion. If a buoy is displayed as gray, meaning that the data was unavailable, it doesn't necessarily mean that it doesn't exist. It just might not have been there at the time of collection. So if you're interested in a specific location, please go to the respective source website and check it out for yourself, and just to be sure. And then final disclaimer is that these files and the data stored in these files are all in coordinated universal time. So that means that there's going to be a time shift between local time for us being Central Standard Time and the files. So in order to find out the time of the file in your time zone, you have to add or subtract the appropriate amount of time depending on your location and the time of the year. I included the same URLs that are on the HTML page, as well as the link to my presentation, and then just some closing remarks explaining why this project happened, the programming platforms that I've used, and just encouraging users to reach out with any questions, comments, concerns, recommendations, or just to tell me how the file has been used. Any feedback is good feedback. So without further ado, I will navigate here. I'm going to start by downloading this file from last night at 11 p.m. to show you what they look like when everything is working properly. Very similar. I just downloaded the file, and then since I have Google Earth Pro on my computer, it was as simple as double-clicking the file that downloaded to open. So as you can see, we have a little bit of red, yellow, and green, as well as some gray. Our color bar shows, the color map shows quite nicely. You can even see underwater ridges. And then now, however, I'm going to navigate back to this site and show you this file, because this is a great example of what it looks like whenever the HiCom data does not work. It does not display the color bar or the color map, and everything is gray. So, like I've said, the system currently has a glitch that I will be working out. Not sure what's going on there, but I don't expect it to be anything major. I was able to run it on my own, so it might have just been something with the cron tab. But now that you've seen all of this and how to open the files, I'm going to navigate back to my PowerPoint and just end with conclusions that the data retrieval, manipulation, visualization, and interpretation process is pretty time consuming. I presented my scientific question and answer to you, as well as my idea of how this process could be automated. I showed you a way to store this data in a very user-friendly manner. Most people know and understand Google Earth or Google Maps or some sort of Google program. I showed you my website and gave you a brief tutorial. So I thank you so much for your time. Here are a list of my sources that I used for this presentation. And now, if anybody has any questions, I'll be glad to hear them.